For decades, astronomers have trusted their equations more than their eyes, and those equations have been screaming that something is wrong. The problem begins with a number scientists thought they understood. When cosmologists measure the aftermath of the Big Bang using the faint glow of the cosmic microwave background, they can calculate how much ordinary matter the universe should contain. Not dark matter. Not dark energy. Just the normal stuff made of atoms, gas, dust, stars, galaxies. The kind of matter that shines, absorbs light, and leaves fingerprints across the electromagnetic spectrum. These measurements are astonishingly precise. They tell us exactly how many atoms were created when the universe was young. And yet, when astronomers go out and count everything they can actually see today, nearly 40% of that matter is missing. Not misplaced, not hidden behind dust. Gone. This is what makes the problem so unsettling. Scientists are not guessing that the matter should exist. The early universe itself recorded the evidence. The cosmic microwave background acts like a receipt from the birth of the cosmos, locking in the amount of normal matter with incredible accuracy. If that missing matter truly did not exist, then our understanding of the Big Bang would collapse. The universe would be lying about its own origins. And yet, every survey of galaxies, every census of stars, every measurement of intergalactic gas comes up short. The universe looks lighter than it should be. Either the matter is out there, hiding in a form we can barely detect, or the foundations of modern cosmology are deeply flawed. And the strangest part is that this was not the first time the universe hinted it was keeping secrets. Long before scientists realized that ordinary matter was missing, galaxies themselves were already behaving suspiciously. When astronomers studied massive clusters of galaxies, they noticed something that should not have been possible. The galaxies inside these clusters were moving far too fast. According to gravity, they should have torn themselves apart and scattered into space, but they stayed bound together, as if held by an invisible hand. This was not a small discrepancy. It was a glaring contradiction between observation and theory. Something massive was there, exerting gravity, but producing no light. Later, similar behavior appeared inside individual galaxies. Stars near the outer edges of spiral galaxies were orbiting just as quickly as stars near the center. By all known laws of physics, those outer stars should have drifted away into the void. Instead, they remained locked in place. Astronomers were forced to accept a disturbing conclusion. The universe was filled with something unseen, a form of matter that does not glow, does not reflect light, and does not reveal itself easily. This invisible influence shaped galaxies, controlled their motion, and quietly dominated cosmic structure. And as scientists would later realize, it was also hiding a key piece of the missing ordinary matter. The universe wasn't just hiding matter inside galaxies. It had a far more intricate secret. Scientists began to realize that galaxies are not scattered randomly through space. Instead, they are strung along vast, invisible structures stretching across millions of light years. This framework, known as the cosmic web, acts like a skeleton upon which all galaxies are arranged. Filaments of dark matter form the backbone, with gas and ordinary matter clinging to them. Simulations suggested these threads extend for tens to hundreds of millions of light years, connecting galaxy clusters like beads on strings. Where the filaments intersect, the densest regions form nodes that host hundreds or thousands of galaxies. The concept of the cosmic web was born from computer simulations long before it could be observed. Slight variations in density from the early universe, visible in the cosmic microwave background, dictated where matter would collect over billions of years. These tiny fluctuations guided the formation of large-scale structure, allowing filaments to emerge naturally in models. What scientists could not yet see directly, however, remained a mystery. The web was there in simulations, hiding in plain sight, and it might be concealing not just dark matter, but also the missing 40% of baryonic matter that had eluded detection for decades. Predictions are one thing, but proving the cosmic web exists proved far more difficult. For years, astronomers relied on indirect clues. Gravitational lensing allowed them to see how the invisible mass bent light from distant galaxies. Quasars, extremely bright cosmic beacons, illuminated hydrogen gas along filaments, offering tantalizing hints. In 2012, 18 Hubble images were combined to infer a filament funneling matter into the galaxy cluster MACS J717. The evidence was there, but it was never a direct detection. Scientists were looking at distortions, shadows, and faint glows. Every observation brought them closer, yet the true filaments remained elusive. In 2014, Sebastiano Cantalupo's team observed hydrogen gas filaments illuminated by a distant quasar, revealing part of the cosmic web for the first time. The filaments spanned millions of light-years, but even these detections relied on bright cosmic flashlights. Typical filaments, faint and diffuse, remained hidden in darkness. For the missing baryons to be found, astronomers needed a way to isolate faint, hot gas from the cosmic background and separate it from bright sources, like supermassive black holes. The challenge was immense, but every near miss built the path toward a true breakthrough. After decades of almost seeing the cosmic web, technology finally caught up, and the universe was ready to reveal its secrets. Around 20 years ago, astronomers began moving beyond indirect hints and statistical evidence. In 2012, using quasar illumination, they could glimpse parts of the cosmic web in hydrogen gas. But these filaments were far from the missing baryons scientists were seeking. The real challenge was detecting hot, low-density gas, the kind predicted to hold the universe's missing visible matter. To do this, astronomers needed instruments sensitive enough to detect faint X-ray emissions and the ability to remove interference from other cosmic sources. It was a task that required precision, patience, and cutting-edge technology. Progress came slowly. Teams worked tirelessly to separate the faint glow of diffuse gas from background X-rays produced by supermassive black holes and other energetic phenomena. Each failed attempt refined the methods and sharpened the instruments. Finally, in 2023, a dedicated instrument at the W.M. Keck Observatory in Hawaii succeeded in isolating dim Lyman alpha emission from hydrogen filaments. This breakthrough allowed scientists to produce three-dimensional maps of filaments in unprecedented detail. Suddenly, the cosmic web was no longer just a simulation or a shadow it could be measured. And then, in June 2025, astronomers saw what they had been hunting for across decades. Using JAXA's Suzaku X-ray Space Telescope combined with the XMM Newton Observatory, a European team led by Konstantinos Migkas mapped a single filament of hot gas connecting 4 galaxy clusters in the Shapley supercluster. This filament stretched an astonishing 23 million light-years, roughly 230 times the size of the Milky Way, and contained about 10 times the mass of our galaxy. Its temperature was scorching, 10 million degrees Celsius, revealing a dynamic structure that had remained hidden until now. The filament's appearance was striking. In X-ray maps, the galaxy clusters appeared as bright white spots, while the hot gas forming the filament extended between them in a band of purple, creating a honeycomb-like pattern. This was exactly what cosmological simulations had predicted, confirming that the cosmic web not only existed, but was actively connecting massive structures across the universe. For the first time, astronomers could see the universe's missing ordinary matter bound within these filaments, hidden in plain sight for billions of years. It was as if the universe had been patiently waiting for humanity to build the tools capable of seeing its bones. The detection of the Shapley supercluster filament provided more than just a spectacular image. It was a critical test for the lambda cold dark matter model, the standard framework scientists use to describe the evolution of the universe. According to this model, dark matter forms the backbone of large-scale structure, guiding the accumulation of visible matter along filaments. Until now, direct evidence for both the cosmic web and the location of missing baryonic matter had been sparse. This discovery aligned almost perfectly with the predictions of large-scale cosmological simulations, showing that our understanding of how galaxies, clusters, and filaments form over billions of years was remarkably accurate. Yet scientists are cautious. One filament, no matter how massive or detailed, is not enough to fully prove that the universe behaves exactly as our models predict. There are still countless structures to map, and the properties of hot gas, dark matter, and the interactions between them need further confirmation. Still, this breakthrough marked a turning point. The 40% of ordinary matter that had eluded observation since the Big Bang had finally been located, and it appeared in the place that theory had long suggested. The cosmic web, once a hypothetical scaffold, had revealed itself in living color. The universe is vast, and one filament is only the beginning. The next step is to see the web in its entirety. The European Space Agency's Euclid mission, launched in 2023, is poised to take this exploration to the next level. Euclid is designed to map the three-dimensional structure of the universe with unprecedented precision. By measuring the shapes of millions of galaxies and the distortions caused by dark matter, it will reveal where invisible filaments thread through space. Redshift measurements will provide a 3D position for each galaxy, allowing astronomers to infer the location of dark matter filaments and the ordinary matter they contain. By comparing these results to previous observations, such as the XMM Newton filament detection, scientists hope to map much of the cosmic web and test the Big Bang model like never before. If Euclid's findings match theoretical predictions, it would be one of the strongest confirmations of the lambda CDM model in the history of cosmology. If discrepancies appear, it could point to new physics, a misunderstanding of dark matter or gravity, or even something unexpected about the early universe. Either way, we are entering a new era of precision cosmology. By 2030, humanity may finally have a full blueprint of the universe's skeleton, revealing how galaxies, clusters, and filaments are woven together and where the missing ordinary matter truly resides. The universe has been hiding its secrets for billions of years, but we are finally learning to read its invisible architecture. Even after billions of years, the universe still keeps some of its most profound secrets just out of reach. Finding the missing matter was a monumental step, but it also reminds us how much we have yet to understand. The cosmic web stretches across unimaginable distances, quietly holding galaxies together and shaping the universe we see today. The fact that 40% of ordinary matter could hide for so long, only to be revealed with the right instruments, shows that the universe often waits for us to catch up. And this is just the beginning. Filaments, clusters, and dark matter still weave patterns we have barely begun to map. Missions like Euclid promise to reveal even more of this hidden framework, potentially rewriting what we know about gravity, dark matter, and the history of the cosmos. Every discovery brings new questions. What other invisible structures govern the universe? How do they influence the evolution of galaxies, stars, and even life itself? The story of the cosmic web is far from over. It teaches us that the universe is patient, mysterious, and full of surprises. It challenges us to keep looking, keep building better instruments, and keep asking the bold questions that push science forward. One thing is certain: the universe is far stranger and more intricate than we could have imagined, and we are only beginning to uncover its hidden skeleton.